Okay, any other questions? All right. So this is how we're going to use it to start with. This is our first control algorithm. So prediction is how you learn a value function, but we want to actually learn a policy. We want to use reinforcement learning to learn a policy. And this is Monte Carlo policy learning, and it's called on policy Monte Carlo control. And it's Monte Carlo because we have this sort of sequence of a trajectory of state action reward pairs, tuples, and we're going to learn from that. So we start with the parameters of the algorithm are, it's epsilon, right? Thing we saw previously. And we start with some arbitrary policy. So we start with some policy where effectively we've picked some greedy action at random. Right, so we pick some greedy action at random in each state, but this is an epsilon soft policy, which I said at the beginning. That means there's some probability that we can choose every action. Does anyone want to suggest why that's important? Why do we need to have a soft policy that has some probability of choosing any action, rather than a policy where some of the probabilities are zero? It says that there is no zero in any of this. So when we have a policy and we have something like this, if you look right at the bottom, that's the policy saying what's the probability of taking action A in state ST. And a soft policy will never return zero at that point. We'll never have a zero there. So, and it's really important in this algorithm, or in reinforcement, that we don't have zeros. Any ideas?
I think earlier you mentioned that there is exploitation versus exploration. So if it is zero, it belongs to one of this. Totally, I forgot which one is this.
Yeah, that's close to the right answer. So if we have a zero there, then there's no chance to explore that action. Right, we must be able to, in order for this to converge to the optimal policy, we must be able to try all actions. And if we can't try all the actions, then there's a chance we miss finding out about the optimal policy. So that's why we must have a soft policy. But in general, this algorithm is pretty similar to the value prediction algorithm we saw last time. So what we do is we generate an episode using our policy, right? So our policy is there, and this is one episode in the environment. So this is our robot walking around doing stuff. And at the end of the environment, we have this episode, we have this state action reward triple sequence. And then the algorithm starts at the end of the episode and works backwards. And at each step, for each time step, we compute the future discounted return. If you remember, that's the sum of the rewards we get in the future, with the discounting as well. And then we take the average. So what we do is we append the sum of to the returns. So if you remember, this is like a list where I've got a bunch of G's. So this is like the list of returns for S. So for a particular state. In fact, for state action. So for every state action pair, I have one of these lists, and in that list is a sequence of the returns I got from that state. Okay? So I've got this list. Every time I see a state action pair, I add the discounted expected reward to the list for that state action pair. The reason I do that is because then I compute the Q value. I compute the Q value for that state action pair by taking the average of that list. Okay, that's the list. I take the average over the list, so I sum it all up and divide it by the length of the list. And then I decide what is the action I take, what is the greedy action, and that's here. So this bit is saying what is the greedy action. And then I use that to decide what does my policy look like. Okay, if it's the greedy action, then I have some probability of exploiting. And if it's not the greedy action, then I explore. Then I set up the exploration probabilities. So that bottom line defines the policy we're going to use. And then, of course, what we do is we loop back up and generate a new policy, right? We've updated our policy, and then we loop back up and we use this policy to create a new trajectory through the environment. So this is super important. We start with an arbitrary policy, right? A policy that is making bad choices. We execute that policy in the environment. We can then use the trajectory to update our Q values. And then we can update our Epsilon soft policy with those Q values estimates. And then we repeat that. And every iteration, so every repeat, our policy should get ideally a little bit better. There's no guarantee that in one iteration it will, but in the long term, we should get a better policy. We will get a better policy. And given infinite time, we converge to the optimal policy. So much like value iteration, we don't know with value iteration how many episodes how many iterations we need to run. And it's the same with reinforcement learning. There's no way for us to tell in advance how many repeats we need to converge to an optimal policy. But we know on policy Monte Carlo will converge to the optimal policy given enough time. And that's because given infinite time, we try every action an infinite number of times. So therefore, we're guaranteed to converge to the true values. There's no convergence criteria. So we don't have residuals and things like that like we did in value iteration. What you typically do, what most people do, is they look at the value of the policy, so the expected value from across the initial state distribution. And at some point, that will not change very much. So typically, it will always change. But you can see by looking at the rewards the policy receives that at some point those rewards roughly plateau. And at that point you go, okay, my policy is converged. But there is no way to tell for sure if your policy is converged. It's the same with value iteration. You would typically use some kind of residual-like mechanism, but in general you think the longer you go, the better your data. And the reason for that is you may have some very, very high reward action that is only available in some state you reach with very low probability. And if you don't ever see that, because this is a sample-based method, the probability of sampling that very rare outcome is very, very low. So you might need thousands or millions of trajectories to actually take the right sequence of action choices that lets you see that very high reward but low likelihood outcome. And so things like that can really change your value function. But you may, because you're doing this in a sample-based way, you may not see it very often. And then to see it enough times to make the estimate of that value, the average value, correct, is also a challenge.
So with this this algorithm and the earlier one, value iteration. So here, can we say the main difference following could be like value iterations? They have residual. Sorry, what's the word? I can say that clearly.
Residual, yeah.
Residual, as well as that this one can run for really infinite number of time.
That's not the important difference, though that is a difference.
Okay.
The main difference, with the most important difference, is that value iteration requires access to the true value, the true reward function.
Oh, right.
And the transition probabilities.
Okay, right.
Here, there is no P and there's no T. So
a lot of things are, unseen to the algorithm. So it has to work in the real world and learn them.
Yeah, the only time we get to see any of these is we get to see samples and we see sample trajectories. Okay. So we just get individual data points. We don't get the whole function.
Okay, thank you.
And there's a lot of people who would argue that it's very rare to get that whole model. And it's, this is a more realistic setting. I think the truth is somewhere between the two extremes, but I think it's an open question in robotics and AI, really. If you've got the functions, you can do a lot more. But if you don't have the functions, then you're kind of forced to do reinforcement.
So it's like that if I don't know the functions, then most probably I would go ahead with reinforcement learning. Is it?
Yes, in general. Okay. Because sometimes what you might do is so what actually people tend to do in, if it's a very high risk domain, you might have an existing hand-built controller that is neither planning nor learning, but is an expert who has written down a set of rules to control the robot or to control the process.
Okay.
And then that process, you can think about that process as generating data in trajectories, but crucially, that data is not drawn from the distribution of some policy. And we'll talk about something a bit like that in a minute. But you might have trajectory data from a system, and you can use that trajectory to try and learn a model and then do planning. Or you might try and learn a policy using the data offline. So those are quite common ways of actually getting started in the real world if you don't have the function, but you have a system that actually acts in the world.